What are neural networks? Neural networks remain a cornerstone of modern machine learning and artificial intelligence, offering unparalleled capabilities by drawing inspiration from the human brain's functionality. As tech professionals, understanding neural networks is essential to leverage their full potential in solving complex problems. Modeled after neural structures, artificial neurons, or nodes, interconnect within a network to learn from vast datasets. This learning process allows machines to identify patterns, make precise predictions, and refine their output over time, making neural networks indispensable for advanced machine learning applications. The input layer acts as the network's data entry point, where each node signifies a feature of the data being analyzed. In image recognition, for instance, input nodes might represent individual pixel values. For tech professionals, it's crucial to understand that the quality and structure of the input data significantly influence the performance of the entire network. Situated between the input and output layers, hidden layers are where intricate data transformations occur. Through weighted sums and activation functions, these layers adjust internal parameters to enhance the network's accuracy. Nonlinear activation functions, such as ReLU and sigmoid, empower networks to tackle intricate problems. Technologically inclined individuals should note that the depth and number of hidden layers are pivotal in defining a network's complexity and capabilities. After traversing all hidden layers, data reaches the output layer, which yields the network's classified result or predicted value. In classification tasks, outputs may be distinct categories, whereas regression tasks may produce continuous values. Recognizing how output interpretations depend on task type can guide the refinement of neural network designs and applications. In forward propagation, data navigates from the input layer through successive layers until reaching the output. Each layer applies specific weights and biases, followed by an activation function, culminating in the network's prediction. Mastery of this flow is essential for troubleshooting and optimizing neural network performance in tech-driven environments. Neural networks learn by minimizing the discrepancy between predicted and actual outputs through backpropagation. This involves calculating errors and iteratively adjusting weights using the gradient descent algorithm. For tech experts, exploring different optimization strategies and learning rates can be crucial for enhancing neural network training efficiency. Training involves fine-tuning network parameters across numerous iterations known as epochs, using datasets of input-output pairs. The goal is to reduce error and hone prediction accuracy. Utilizing diverse datasets and robust training practices can substantially impact a network's generalizability and performance. Feed-forward networks, characterized by unidirectional data flow, excel in straightforward tasks like image classification, devoid of loops or cycles. Their simplicity can often be advantageous, particularly when computational efficiency is a concern. Designed for grid-like data analysis, CNNs employ convolutional layers to detect specific patterns, vital for tasks like object detection and facial recognition. Proficiency in CNN architecture is indispensable for tech professionals working on image-intensive projects. RNNs specialize in sequential data analysis, as seen in language modeling or speech recognition. Their ability to retain prior information makes RNNs ideal for context-dependent tasks, which is particularly useful in natural language processing. DNNs feature numerous hidden layers, underpinning sophisticated AI applications like autonomous driving and AI creativity tools. Their deep structures enable complex pattern modeling, but they also demand significant computational resources and expertise. Neural networks have revolutionized image recognition, powering systems that can diagnose medical images as adeptly as human experts. In speech recognition, they drive assistants like Siri and Alexa, processing spoken language with remarkable accuracy. Natural language processing benefits from neural networks' ability to analyze and generate human language, enhancing chatbots and translation services. Neural networks also enable autonomous vehicles to make informed driving decisions based on sensor data and advance healthcare through precise diagnostics and patient management. What are neural networks? Effective training necessitates vast labeled datasets, which can pose logistical and financial challenges. Tailoring strategies to optimize data acquisition and preprocessing can alleviate these challenges. The demand for robust computational resources to train deep neural networks remains a significant hurdle. Access to cloud computing solutions and parallel processing can mitigate these constraints. Overfitting, a challenge where networks become too attuned to training data, can be addressed through regularization techniques like dropout. Balancing complexity and generalization is a key focus for tech professionals. The black box nature of neural networks can hinder transparency, particularly in critical fields like healthcare. Striving for explainable AI models can help bridge this gap, ensuring ethical and understandable AI deployment.